So in section 3, we're going to look at a very special type of discrete probability distribution that's called the binomial distribution. And then we'll look at a second one, which is called the geometric distribution. So a binomial distribution is one that just kind of satisfies a very select number of probability problems. So you can see here, we actually can define what a probability experiment is with 4 steps. So binomial meaning 2. A binomial experiment can only have 2 outcomes or things that can only be reduced to 2 outcomes. For example, heads or tails. Maybe getting an A on a test or not getting an A on a test. These would be 2 outcomes. There must be a fixed number of trials. So I have to only ask a certain number of fixed people some question. So the outcomes must be independent of each other, and the probability of success must remain the same for each trial. So if these 4 conditions are the same, then we can find the probability of R number of successes out of N trials. And this is important because it's what's the probability we get so many out of so many whatever. 5 heads out of 20 flips. We can actually find it using this distribution without making tree diagrams and all that long stuff we've done in the past. So we look at some examples here, whether these things are binomial or not. This says surveying 100 people to determine if they like sudsy soap. Well, that would be binomial because you basically do or you don't. There is some probability for people who like sudsy soap, and I'm only asking a fixed number of people. B falls under that same realm that is also binomial. It's how many heads you get. Well, you get heads or you don't. Same probability of getting a head every time, and we're flipping again a fixed number of times. Drawing a card from a deck and getting a heart. Now this is not binomial. Now it is 2 things. It's either a heart or not a heart, but the problem is we're drawing until we get one, so it's not a fixed number of trials as we said in number 2 up here. So you have to have a fixed number of people to ask if it's going to be binomial. Okay, D says asking 1,000 people which brand of cigarettes they smoke. Well, that would not be binomial because there are more than 2 outcomes for what the brands of cigarettes they smoke. Testing a brand of aspirin by using 10 people, so there's our fixed trials, to determine whether it's effective. That is binomial. It's either effective or it's not. There is some effective probability, I don't know what it is, but we ask a fixed number of people as well. F, asking 100 people if they smoke. Also binomial. Fixed number of people. There is a percentage of Americans who smoke, and so we can make that binomial. G says checking the 1,000 applicants to see whether they are admitted to the University of Findlay. That's also a yes because there is some probability you get into the university, acceptance rate or something. We ask a fixed number of people, and that stays the same for every person. Surveying 300 prisoners to see how many different crimes they were convicted of, this would be no, because there are more than 2 crimes. Now, if you look at I, it's kind of a spin on that. It says surveying 300 prisoners to see whether this is their first offense. Well, that would be okay, because it either is their first offense or it is not their first offense. So we kind of know what a binomial experiment is. So now we're going to try to look at some of the examples. Now, before we look at the formula, we just kind of can see that there are a couple different variables we have to define: P, Q, N, and R. So P is the probability of success. So if it's heads, it would be 50%. Q is the probability of failure. So if it's a 70% chance you get something, then it's a 30% chance you don't. So that would be Q. N is the number of trials. How many people am I asking? How many times am I doing some experiment? And R is how many successes I'm looking for. So if I'm looking for, okay, what's the probability of 3 heads when I'm flipping a coin out of 10 coins? Okay. Well then, if I look at these variables, this would be my R, this would be my N, and my P and Q in this case would be the same because they're both 50%. Because it's 50% likely you get ahead or not get ahead. So the formula for this binomial distribution is pretty nice. it actually involves our combination term we see on the last chapter. So the probability of R, and sometimes I like to write it as R out of N. You can see I have it as the combination form here and as the expanded combination form there. But essentially it's going to be N choose R, P to the R power, Q to the N minus R power. Okay, so we're going to take this and we're going to use this to do a couple problems. So this first one says it was found that 60% of Americans victims of healthcare fraud are senior citizens. If 10 victims are randomly selected, find the probability exactly 3 are senior citizens. So in this case, our N, how many people are we asking? We're asking 10 people. Our R, we want to know what's the chance that 3 out of those 10 are, so that's 3. The probability a victim of healthcare fraud is a senior citizen is 0.6. So the probability they're not is going to be 0.4. So the probability we have 3 out of 10, we just use the formula. So we'll do N choose R, so that's 10 choose 3, times the probability they are, that's 0.6 to the 3. Because to the R, and then Q is 0.4, and we do that to the N minus R. So basically, if 3 are, it's how many aren't, and there's 7 that aren't. And so this is something that we can be just put in our calculator and see what that probability is. So that probability is going to work out to be 0.0425. So make sure you can get that in your calculator. Pause the video if you need to, just to make sure that you get that same probability that I did. Okay. Okay, let's go ahead and look at another example. This says a burglar alarm has 6 fail-safe components, so we know N is 6. The probability of each failing is 0.05. So our P is 0.05. And our Q, all right, Q is going to be 0.95. So this first example says, what is the probability exactly 3 will fail? So I'm going to write that as the probability 3 out of 6 fail. So if we write the formula, that's going to be 6 choose 3 times the probability, which is 0.05, to the third, because that's how many we want to fail. And then the leftover, of course, be 3, so that's 0.95 to the 3. So if we put that in our calculator, we will get, so that is 0.002. So not a very good chance that 3 out of these 6 fail, which is good because you don't want your burglar system to fail. So if we look at B, we have the probability of 0 out of 6 failing. We want them all to work, essentially. Same idea. We'll do 6 choose 3, or sorry, 6 choose 0 this time, times 0.05 to the 0, because we want none of them to fail, and 0.95 to the 6, because we want them all to not fail. So if we do that, I get a probability that is very high, which is good because we don't want these to fail, 0.375. Now, so last example says, what's the probability that fewer than 2 will fail? So let's look at the last one. It says the probability that fewer than 2 will fail. Now, fewer than 2, so we have to think about what fewer than 2 means. Well, fewer than 2 means under 2, so that would simply be 1 or 0. So all we have to do is we'll just take those individual probabilities and we'll do them together. So 0 out of 6, which we already know the answer to, and the probability of 1 out of 6. So we have to find what those probabilities are. So we know the probability of 0 out of 6 from part B. So that's 0.735. And so if I do the 1 for 1, that's going to be 6 choose 1, 0.05 to the 1, 0.95 to the 5. And I'll put that in my calculator, so I'm getting 0.735. And if I put that in, I get 0.232. So if I add that together, I get 0.967. So there's a very high probability that less than 2 of them will fail, 0 or 1, which is good, because again, we don't want the burglar system fail-safe components to fail. All right, let's look at one more example of kind of binomial probability. This says, according to the Information Almanac, 80% of adult smokers started smoking before they were 18. So that's telling me this probability for all American, well, all adults anyways, who smoked, started before they were 18. So P is 18 or 80. So Q is 0.2. And this problem says we're sampling 10 smokers. So we know these people smoke, so we know that 80% of them in general started smoking before they were 18. So this is a binomial experiment because there's two outcomes, right? It's either yes, they do before 18, or no, they don't. Consistent probability, 0.8, and a fixed number of trials being 10. So question B, or part B says, all right, find the probability exactly 8 of them started smoking before 18. So that's the probability of 8 out of 10. So if I put that into the formula, we have 10 choose 8 times 0.8 to the 8, and then 0.2 to the 2. Because we said 8 of them are, that means 2 of them are not, and that's what the n minus r is for that second part. So I went ahead and tossed that in my calculator, and I'm getting a probability of 0.30199. So a little over 30% chance that 8 out of those 10. Now 8 is the most likely number because 80% of 10 is of course 8, so that would kind of make sense that that would be the largest number. So this C is a little trickier. It says, what's the probability that at least 8 of them started smoking before 18? Now if you think of what the word at least means, it means 8 or more. Now, since this is a discrete distribution out of 10, that does kind of limit how many we have. So 8 or more is going to be 8 or 9 or 10. So this is going to take a little bit more work because I'm going to have to take what's the probability of at least 8. I'm going to have to actually find 3 probabilities and add them together. So that's going to be the probability of 8 out of 10 plus the probability of 9 out of 10 plus the probability all 10 started smoking before they were 18. So it's kind of a very repetitive formula. 10 choose 8 times 0.8 to the 8 times 0.2 to the 2. We actually have that probability. That's the first one. Plus 10 choose 9 times 0.8 to the 9 times 0.1 to the 1 plus 10 choose 10 0.8 to the 10. You can put 0.2 to the 0, but you really don't have to because we know that just kind of doesn't figure into the probability. So I'm going to put these into my calculator. I'll do them individually. So for 8, I know I get 0.30199. For 9, I'm getting 0.26844. And for 10, I'm getting 0.10737. And again, these are or because it's 8 or 9 or 10. So that's why I am adding these probabilities together. So if I add those together, I am going to get 0.6778. Okay, so now if I go ahead and I look at D, D gives us kind of a problem that would be very difficult, but if we use our know-how, we can actually make it pretty easy. So it says find the probability that fewer than 8 smoke, or started smoking before 18. So the probability that fewer than 8, well, we just talked about that with the burglar alarm on the previous problem. that's going to be less than 8. So that's going to be 0, or 1, or 2, or 3, or 4, or 5, all the way up to 7. So that is a lot of probabilities to calculate. We'd have to calculate 8 probabilities to find this. But I'm going to say that I don't have to calculate any probabilities because I can actually use the complement. Because the probability that there are fewer than 8 is the exact opposite of being 8 or more. So all I have to do is take away 1 minus the probability of 8 and above. But we know what 8 and above is because that's what we did for the previous part. So all I have to do is 1 minus 0.6778 to get my probability. So that's going to be 0.3222. Last one is very similar. It says find the probability between 7 and 9 of them inclusively started smoking. So that's inclusively means we're going to be between 7 and 9. So since it's discrete, remember there's no numbers between 7 and 8, so it's just basically the probability of 7 out of 10, 8 out of 10, 9 out of 10. And we know a lot of these probabilities. I know 8 from above is 30199. We already did a 9, that's 0.26844. And if I do 7, that if I put in, remember it's going to be 10, choose 7, 0.8 to the 7, 0.2 to the 3. So if I put that in the calculator, I'm getting 0.20133. And so I'll just add those numbers together to see what my total is. 201. So the sum of this is going to be 0.77176. So that's going to be my probability for between 7 and 9. Now, if you remember, we actually had those longer formulas to find the mean and standard deviation for probability distributions. The x's times the p of x's, and these x squareds times the p of x's minus the mean squareds. Well, the cool thing for binomial distributions and later on geometric distributions, there are very simple formulas for the mean and the standard deviation. The mean of the binomial distribution is just NP. So that's the average number you'd expect. So very simple, just the number times the probability. The variance is NPQ, so you take the number times the probability it doesn't happen. And then the standard deviation is, of course, the square root of the variance. So if we look at a quick example of this, it says it's been reported 83% of federal employees use email. So we know the P equals 0.3. So that's going to make Q equal to 0.17, so 17% of people don't. So we are a sample of 200 federal employees. So now we are going to find the mean, variance, and standard deviation of this distribution. So the mean is going to be 200 times 0.83. So essentially we're just trying to figure out what's the average number of employees that you'd expect in a sample of 200 to use email, which we also remember we called the expected value. So 200 times 0.83 is 166. The variance, which is so this would be employees, right, for our units. So the variance is NPQ, so that's 200 times 0.83 times 0.17. So the variance is kind of a weird number. It's 28.22, but remember, variance, it'd be square employees, whatever that is. And so the more important one is the standard deviation, which we can simply take the square root of. So the square root of 28.22 will give us 5.31 employees. So what I know about this situation is I know if I take a lot of samples of 200 federal employees, I'd expect that about 166 out of those 200 to use email, and those results would be off by about 5.31 employees on average. So some samples would have more, some samples would have less, but on average they'd be off by about 5.31. So that's kind of the binomial distribution, how many out of how many. So we're going to look at another distribution, which quite honestly the formula is very simple, a little more straightforward, but it finds a totally different thing. So our probability of finding r successes in n trials was our binomial. That's what we just did. So the geometric is going to do a totally different thing. It finds out what is the probability of getting our first success on the nth trial. So if I'm flipping a coin, I might ask, what's the probability the first time I see a head is on the 8th flip, or 9th flip, or 10th flip? So something a little different. So the probability of getting the first success on the nth trial is simply p times q to the n minus 1. So very simple. So you take the probability of it happening times the probability of not happening to the n minus 1 power. We also have a mean and standard deviation. These are not used quite as often as the binomial one. We use that a lot more often. But you can see the mean is 1 over p. So that's what you'd expect. Expected value, mean, same thing. And the standard deviation is square root of q over p. Okay? Okay, so let's look at some examples. So it says O negative blood can be given to anyone else regardless of the recipient's type. Only about 6% of people have O blood. So the probability of having O blood is 0.06. So the probability of not is, of course, going to be 0.94. So if I want to know what the probability the first donor has O negative blood, so remember the probability for a geometric distribution, the probability of the first successes on the nth trial is p times q to the n minus 1. So in this case, that's going to be 0.06 times 0.94 to the 1 minus 1. So if I work this out, this actually turns out to just be 0.06. And that kind of makes sense because if you're the first one, then the chance you have that blood is 0.06. So the probability of being the first success on the first trial is simply just p. So let's look at B. B says, what's the probability of one of the first 4 donors? So one of the first 4 donors could be the first success on the first trial, or, so I add, success on the second trial, plus it could be on the third trial, plus it could be on the 4th trial. So we're going to simply sum those probabilities. So the probability it happens on the first, we already know, that's 0.06. Now the probability that the first success is on the second trial, that means it's no and then yes, is going to be 0.06 times 0.94 to the 2 minus 1, which is just 1, plus 0.06 times 0.94 to the n minus 1, so that's going to be 3 minus 1, which is 2, plus 0.06 times 0.94 to the third. So if I add all those up, do those individually, I get 0.2193. So still not very likely because, you have a lot of failures. It's not very likely to have O blood, so it's more likely to not have O blood. Now we can actually figure out when we'd expect to see the first one because obviously not very good chances in the first 4. So if we ask how many can you expect to process before you find someone with no blood, remember expected value is the same idea as a mean. So all we're going to really figure out what the expected number you'd have to see before you find an O negative blood is just 1 over p. So 1 over 0.06 is going to be 16.67 people. So on average, you'd have to look at almost 17 donors before you'd find one with O negative blood, assuming all the people randomly were lined up in some kind of order. So that is 6.3, binomial geometric distribution. Take those notes. Hopefully, if you have any questions, you'll let me know.